Hello everyone and welcome back to science class. Today we are going to talk about how water moves through the different spheres, talking about how it moves on land and how it moves in the ocean. So let's review the water cycle. When the sun shines down on the earth, it warms up the surface waters, not just in the ocean, but in our lakes and rivers and streams and ponds as well. This warming causes the water to evaporate, turns into a gas. Now, when this water vapor comes high enough into the air, it actually becomes cold enough that it condenses back into liquid water. It's still pretty light though, so it doesn't fall out of the sky quite yet. So it condenses into clouds. Now, when these clouds become full enough and saturated enough, that's when we have precipitation happen. The water will fall from the sky in either the form of snow or rain or sleet, sometimes even hail, depending, on the different atmospheric conditions that are happening at the time. But it will fall. When it lands on the land, it will take the path of least resistance. So if it's going to land on top of a mountain, it's going to take the steepest path down the mountain, no problem there. If it lands on a flat surface, there's still a little bit of a grade, there's still a little bit of a slope, so it will take the path of least resistance. I'm sure you guys have seen how water travels on roads. Sometimes it looks like there's divots in the road where the water collects, and then other times there's high spots where the water runs off. The way the water runs off these high spots and into the streams and rivers that lead eventually to the ocean, these are called watersheds. A watershed is an area that collects water, essentially. So you can have a valley that's deep in the mountains, and that's a watershed. Or you can have a large area that's considered to be a watershed that's made up of multiple valleys and divots that just all seem to drain to one area. Now, when water runs off the ground, there are a couple of things that will prevent it from reaching the river at a fast pace or whatever. One of the things is that it can be absorbed by the ground. When it's absorbed by the ground, it will sink into the groundwater and then it will either stay there or it might move a little slower towards the oceans. If there's a lot of vegetation, if there's a lot of plants, then the plants itself will actually prevent the water from moving. You see, plants need water in order to survive. So if it gets into the soil, the plants are gonna take that water and use it for their own benefit. If you have a steep hill versus a shallow hill, the steep hill is going to have a greater amount of runoff than the shallow hill, just because it's steeper, right? That makes more sense. We've all gone sledding before, we've all slid down hills. We know that a steeper hill is more fun to slide down than a shallow hill. So same thing with water. The type of the soil also affects it. So if it's a very rocky, loose soil, it's going to be a lot easier for the ground to absorb the water. And if it's very smooth rock, if it's like bedrock and it's solid, then it's going to collect on the surface a lot easier and it's going to run off towards the streams and rivers. When you have these streams and rivers that collect the water that comes off of the ground, not only do these streams and rivers bring the water to the oceans, but they also bring minerals and salts and soil and stuff like that. You see, when water passes through the river, it erodes the river sides and the river bottom. This causes salts and minerals to dissolve into the water, which then gets carried to the oceans. You ever wondered why inland water is fresh and then the ocean water is salty? That's because by the time it gets to the oceans, the water is carrying a lot of dissolved salts and minerals. So that's why we have really salty oceans compared to inland. Let's talk about how does the water move in the ocean? So we talked about how it moves on land and how it moves through the air, but what about moving in the oceans? We know that there are ocean currents. If you've ever been to the beach, I know that we kind of live far away from the beach, but if you have been to the beach, you've been aware to watch out for undertows and stuff like that. Undertow is a type of current, but it's a very small current. There are actually much larger currents that happen in the ocean. So how do they move? Now, ocean waters are actually separated into 3 different layers. We have the top of the ocean, which is the surface layer. Then we have a layer that is the thermocline, and this is where the temperature of the ocean changes drastically. Then we have the deep ocean. Now, these are separated in terms of temperature as well as their salinity. So how salty are they? The top part of the ocean tends to be the warmest because that's where it receives the sun's energy. It also gets aggravated by the winds. So you would have a lot of movement in the top part of the ocean because of the winds causing it to move. But that movement doesn't necessarily travel all the way down to the bottom of the ocean, especially considering that the bottom of the ocean can sometimes be 2 to 3 kilometers below the sea level. The thermocline is considered to be like the twilight zone. You have very limited light that enters that deep, so it is quite dark. The deep ocean is the darkest. There is absolutely no light that enters in this area. It is pitch black and very cold. What I'm going to be doing in this demo here is I'm going to use this beaker here, the big beaker here, to demonstrate the deep ocean. Now, unfortunately, I can't emulate how cold it is, so it's just room temperature right now. But I am going to put in some salt to indicate that it is salt water, because that's what the oceans are. So I'm going to go ahead, put in a bunch of salt, and go ahead and dissolve that. So this will be my deep ocean. This beaker here is going to be my surface ocean. So what I'm going to do is I'm going to put in a little bit of salt here. And I'm also going to put in some food coloring because we want to be able to see the separation of the layers. So now I just have to dissolve this salty solution. Now, I'm going to take this, and because these are both room temperature, I want this one to be relatively cold compared to this. I'm actually going to bring this up to a boil. So the temperatures are not going to be the same as you would expect in an ocean, but there is going to be a temperature difference. This one's going to be near boiling, and this one's going to be room temperature. So let's go ahead and get that boiling. All right, so this is almost boiling now. So what I'm going to do is I'm going to carefully pour some of this red liquid into this beaker here. Remember, this is our surface layer, and this is the deep layer of our oceans. Now, if you look closely, you can see that the layers are separating. Right here, you can see that this is very red looking, and this is not so red looking. So this is how the ocean kind of stratifies, is that the cold, salty water tends to stay at the bottom, and the warm, salty water stays at the top. You can see it a little bit better now that I've removed the back there. Now, the surface currents are controlled by the winds. So the winds only really affect the top layer. So if I were to stir this a little bit to pretend that I'm like the wind, you can see that there is not a lot of mixing happening at the bottom here. These currents down here are dictated by how salty the water is and how cold the water is, or how hot, essentially. Typically, cold, salty water is going to sink to the bottom, and then warm, less salty water is going to go up to the top. Now, I have here some room temperature fresh water. There's no salt in this water at all, and we're going to see what happens when I pour this in. I don't know if you can see, but there is definitely some kind of mixing happening. This cup of fresh water that was cold symbolizes the fresh water that enters the ocean due to the melting of Arctic and Antarctic ice. As you can see, when the cold water that was fresh mixed in here and poured into the water, it mixed everything up and it caused a slight difference in the layering. You can see that the bottom here is a lot darker now. So the melting of Arctic ice and Antarctic ice actually disrupts how the oceans stratify, and it disrupts the ocean circulation. So to summarize, the top part of the ocean is called the surface ocean. The surface ocean is mixed by the wind patterns that happen on the surface. Then you have a layer called the thermocline. This is like the twilight zone. There's not a lot of light that penetrates here, and this is where the temperature starts to drop drastically. Right underneath that layer, you have the deep ocean. Now, the deep ocean has currents as well. These currents are dictated by differences in temperature and differences in salinity. We're going to talk a little bit more about the deep ocean currents and how they work with the surface currents next class. Thank you for listening, and I will see you all next time. Bye!